Let's wait for some time. I think one more person has to come. Okay, we'll continue. So to get the velocity at this position, I can use energy conservation. I choose this as my reference for this potential energy. From this, I measure the height h. So at this point, the velocity is something like v. Okay, here the velocity will be reduced. See v. Okay, so energy at this initial point, it's half mv square. That will be energy, kinetic energy at this point, that will be half m v square. That's the gain in the potential energy. That is this much height. And from here to here, the length is the radius of the circular motion, that is r. And this is sin r. And this length will be r cos theta. So this height will be r minus r cos theta. So the height gained is, so there will be a potential energy corresponding to the height, that is r into r cos theta. So velocity at the bottommost point is known. So this v is a function of theta because that theta is coming here. So the tension will be maximum when the string is at the bottommost point. When the mass is the bottommost point, when it is here, the tension in the string will be maximum. Okay, and the tension will be minimum at the topmost point. So tension is maximum here, and the tension is minimum here. There will be maximum at the bottommost point. And the theta depends I can get from here because here v is also a function of theta. This v is actually this small v. Okay, so v function of theta I can get from here, this one. So from this I can, tension is also a function of theta, depending on the position. So at this position, the tension is maximum. Now the topmost point, the tension will be minimum. Any doubts? But in the horizontal circular motion, tension is same everywhere at any position. Sorry, not this one. This one. Horizontal circular motion, because gravity is perpendicular to the spring. Okay, so it do not affect. So the only force is the tension force and the centripetal acceleration. So tension is always constant, and V is also constant. But here, V will change because it's gaining height. Once it's gaining height, it will lose velocity. Okay, so V is a function of position theta. So tension is also a function of position theta. Okay, so for vertical motion, tension is a function of the position of the mass. That is function of theta. Okay. So friction force is a self-adjusting force. This I told for example, there is a mass on this rough surface. So if there is a force, depending on the suppose I apply a force in this direction, then the friction force will be towards left. But suppose I apply the force in the opposite direction, like this, say F2, then the friction force in this particular second scenario will be towards right. Okay. Another thing is even the magnitude of the friction force, it's not constant. Like suppose this surface has got some mu, and then it has got some mass and the normal reaction. So this friction force will be mu into normal reaction. This actually is towards the maximum friction force. Suppose, for example, it turns out to be, say, this is 5 Newton, okay, and I apply a force of 2 Newton towards right. In that case, the friction force will be just 2 Newtons to oppose this applied force of 3 Newtons. But when I increase this applied force to 3 Newtons, then the friction force will also increase to 3 Newtons, just to balance this applied force. And this will happen until 5 Newtons. But if I increase the applied force to 6 Newtons, then the friction force maximum value is 5. Okay, in that case, the friction force will be 5 only. So the net force towards right will be 6 Newton minus the friction force is 5 Newton. That will be equal to mass into acceleration. So the remaining 1 Newton will give an acceleration. So the friction force is function. I mean, even the magnitude will keep changing and it reaches the maximum. And also the direction of the friction force is not fixed. It depends on the external applied force. It can be in the opposite direction also. So here I'm applying the force in the towards right. So friction force towards left. If I apply the force towards left, then the friction force will be towards right. So this is what is meant by the friction force is self-adjusting force. Like depending on the external thing, it will change its magnitude or also direction. Another example is I have an inclined plane and say there is a mass here. So now what is the direction of the friction force? It will be upwards. You will try to slip down. Obviously, try to slip down because the component of weight will try to pull it down. Okay, so in that case, the friction force will be upwards. But suppose I had a applied external force, applied force in this direction, F, and this F is greater than. So here there are two forces, right? One is mg sine theta, which is the weight component, which is putting it down. So, so if it, mg sine theta is greater than the applied force, then the net force is downwards. The net force is downwards, which is F mg sine theta minus the applied force. So this will be downwards. So then the friction force will be up. But if the F values increase beyond a certain limit, then the net force will be in the upward direction. That will be F minus mg sine theta when F is beyond a certain value. So in that case, the friction force will be down. So here you can see the same surface, same mass. So depending on the external condition, the direction of the friction force is changing. Okay. So this is what is meant by the friction force is self-adjusting force. It is adjusting both in magnitude and also the direction. But basically the friction will oppose the relative motion. When the applied force is less, the weight will try to pull it down. So the friction will not allow to go down. So the friction force will act upwards. But when the applied force is large, it will try to go up. In that case, the friction will try to oppose that motion. So it will try to act downwards. So the direction of friction force will change depending on the external condition, but it will oppose the relative motion. So that's what is meant by friction is a self-adjusting force. Okay, so if I have mass on the floor, one way to move it is I can apply a use of pushing force. Another way is the same mass, and I can pull it. Okay, so the surface is same, so mu is same. So given mass, mu, and everything, I can find a F minimum in the first case to make it move. Because if it is very small, means it will not move. After keep increasing F gradually, there will be minimum value after it start moving. In the second case, there will be some F min 2, let me call this F min 1, which will make it move. Okay, so it will turn out that the F min in the second case is less than the F min in the first case. Because in the first case, the friction force is more. So the friction force which will oppose the motion will be in this direction, the friction force, which is equal to mu T(n). In this first case, the normal reaction is one force that is pulling it down is the weight. Okay, normal reaction will be upwards. But this force will have a component, say this angle is theta, will have a component cos theta is horizontal. The vertical component, it's F sin theta. In the first case, the normal reaction is mg plus F sin theta. But in the second case, let me make it the same angle theta. Okay, F cos theta is towards right, F sin theta is upwards. So weight is downwards mg, normal reaction n upwards, and this F cos theta component is upwards, F sin theta. So here in the second case, the normal reaction is mg minus F sin theta. Here it is plus, here it is minus. So the normal reaction in the second case, N2, N1 is less. So the friction force in the second case, which is the same mu into N2. Here the friction in the first case will be mu into N1. So since N1 is more, the friction force in the first case will be more. So the Fmin which will try to start this motion will be more. I think I'm getting a mistake here. So Fmin in the first case should be more. It should make it move. So Fmin, the minimum force will try to move this object is more in the first case. Because the friction force in the first case is more. Because the applied force, a component of it is downwards, which will increase the normal reaction. Once the normal reaction increases, the friction force mu into normal reaction will increase. But here the applied force, a component of it is lifting it, so it will reduce the normal reaction. So here the friction force is less, so the minimum force required to move this in the second case is less. So Fmin in the second case is less compared to Fmin in the first case. Is it clear? Okay.
Yes, sir. Yes, sir.
Yeah. So okay, length of 3D vector already this is same as the Pythagoras theorem in 3D. So length of a vector in 3D is presented as, for example, force vector F. This fx I cap plus fy j cap plus fz j cap. So the magnitude of the vector is square root of fx square plus fy square plus fz square. Okay, so length of the vector is square of the components and then take the square root of the sum. Given RT, the position vector, I can find the velocity and acceleration. This by definition. See, position vector object is given, say R is function of time. So from there I can find the velocity. By definition is rate of change of position. So d by dt of the position vector, it can be a function of time. And acceleration is rate of change of velocity. So it's d by dt of v of t. So for example, let the position vector change like this. Some I cap, j cap, and k cap. So let me make it a function of time. So let's say 2t square, and let this be 3t, and let this be a constant 5. Okay. So for this particular r dependence, I can get the velocity as I and all is not function of I cap, j cap are constant, but they're not function of time. So 2 is also constant. So 2, and the derivative of t square is 2t, and I cap is just remain, and then minus 3. Derivative of t is 1, and then j cap will just remain, and then this will become 0 because phi is constant and k cap is such a constant. It's not function of time, and derivative of constant function is 0. So the velocity is 4t I cap minus 3 j cap. Okay, so velocity is, has got I component is a j component, and the I component is a function of time, and the j component velocity is constant. To get the acceleration, I have to differentiate the velocity. So I differentiate this thing again. So I get 4, derivative of t is 1, so 4 I cap, and the next term is 0. So acceleration is towards the I cap, and the value is 4. Okay, so given a r as a function of time, I can get the velocity and acceleration. Yeah, and this is Newton's second law of motion, force is mass into acceleration, and Newton's second law of motion, force is mass into acceleration, force is a vector, acceleration is also a vector, and mass is a scalar. So given the three quantities, force, mass, and acceleration, given two, suppose mass and acceleration are given, I can find force. Similarly, if other two are given, suppose force and mass are given, then I can find acceleration. Okay. Similarly, if force and acceleration are given, I can find the mass. Okay, this student second law of motion. Work done in compressing or stretching, if I already said it. Work done is integral f dx, and f is kx, and integral of x is x square. So work done in compressing a spring or stretching a spring by an amount x is half kx square. That will get stored as potential energy in the spring. That's also called spring energy. It's actually potential energy in the spring. Projectile motion. Projectile motion, we basically have the earth, and it will project a mass with some initial velocity. So this earth, we can project the earth surface itself. So it's has got initial velocity u, and will be a potential an angle theta. Okay. And since what is the earth is a force which will act on this mass, so there's an acceleration, gravity force downwards. So this motion, I can split as two components. One is this my x-axis, and the vertical one is y-axis. So this is actually a 2D motion. The thing will go like this. So from one point to another point, both x and y are changing. So it's a 2D motion, which is x motion and y motion. So but the interesting good thing is we can analyze the x motion, y motion separately. So y motion, there is an acceleration, which is g, and if we take the upward direction as positive, then this acceleration is minus g, because g is a number which is 9.8 or 10. So acceleration is minus g in the sense like it is in the downward direction. And initial velocity u is u in the y direction is u sine theta. So I can get the maximum height, which is this distance, vertical distance, by using the fact that the vertical component of the velocity at this point, topmost point, is 0. This velocity has got two components. At the initial point, it has got a horizontal component, which is u cos theta, and the vertical component, it's u sine theta. In the horizontal direction, there is no acceleration. Acceleration is 0, because the force is only due to the gravity in the vertical direction. So there's acceleration, because acceleration is nothing but force by mass according to Newton's second law. So to have acceleration, there has to be force. The only force in this problem is the force due to the gravity, which is in the vertical direction. So acceleration is only in the vertical direction. There is no acceleration in the horizontal. So horizontal direction motion is the constant velocity motion. So x displaced in the horizontal direction is the constant velocity, which is u cos theta into the time. So u, the horizontal component, is same everywhere. It will not change. But the vertical component of the velocity will keep on decreasing because something is pulling it down. So initially it's u, so it will keep on decreasing the vertical component. It becomes at this maximum point, the u will become 0. After the direction, u will become downwards. So when it hits, it will become downward velocity. So the initial velocity u component, vertical component of the velocity is say 5 meters per second. When it hits the ground, it will be -5, because downward direction is positive. Upward direction is positive. So initial velocity in the vertical direction is +5. So when it hits the ground, it will be -5. So, and I can find a height using these 2 points. This point and this point. So for these 2 points, b is 0, and then u is u sine theta, and the displacement is this h. So I can use this third equation of motion, which is v square equal to u square plus 2as. Okay, so v is known, which is 0, u is u sin theta. I can find h, which is displacement is not known, that I will find. So this will give me the value of h. Just a minute. So if you put v equal to 0 and u as u sin theta square, and acceleration is minus g and h. So this will be h as u sin theta square by 2g. Okay, so similarly, I can find the time of flight. The time of flight is the time it takes to go from here to here. So that time is capital T. So by symmetry, the time to go from here to the maximum height point will be capital T by 2. Okay, that time I can find by using is equal to qt plus half at square. So if I choose these 2 points, one is the bottommost point and one is the topmost point. So in that case, the displacement will be h, and u is u sin theta, the vertical direction motion. Time is t by 2, and acceleration is minus g, and then t by 2 square. This is becoming complicated. So I can, okay, to get the time of flight, I can use the other one, v equal to u plus at. So v at the topmost point is 0, and u at the bottom point is u sin theta, and acceleration is minus g, and then t by 2. So from this, I'll get the time of flight. Okay, so this is not required. This will make it complicated. So I have found, and then I can find the maximum range of this projectile motion. This is called range of the projectile motion. That is equal to the horizontal velocity, that is u cos theta, into the time of flight. Time of flight is got from here. This one. So if you have to complicate this one, instead of projecting from the ground, I can project this from a height. This is the Earth's surface. So instead of projecting from the ground, I will project from a height. So from this height, I will give it an angle theta. Give it an angle theta. So if you follow the same basic idea of analyzing x and y motion separately, so using the y motion, I can find the time it takes to go from the full path. So this time I can find by using from the maximum, from here to the maximum point, I can use the same thing. First, v equal to v plus v2, right? Yeah. So the time from here to here I can find v equal to v plus at. At the maximum height point, it's 0, and u is u sin theta minus g. Let me call it t1 instead of saying t by 2. The time to go from here to here. Let the time be t1. So I will put that time t1 because this is written between these 2 points. This is the initial point and this is the final point. So that final point v is 0. At the initial point, the u is the vertical velocity, that is u sin theta, and acceleration is minus g. Okay, and the time is t1. So from this, I'll get t1. Hold on. given as u sine theta by g. And then next part T2, that is with this part of the motion. That T2 I can get from this first part, I can also get the height h from here to here, this height h. Okay, so using this previous with this formula, using this formula, I can get h. Okay, using the square by 2g. So that h is known, and this height will be given in the question. Okay, so for now, if I apply this equation motion between this point and this point, okay, so yeah, at this point u is 0 and v is something, and s displacement is h plus h. So if I use s equal to ut plus half at square, and it is time to go from here to here, be t2. Okay, so it become t2. So s will be h plus h, and u is 0, so this term will go, and half acceleration is minus g, and then t is t square, right? So it will be t2 square. So this will give me t2. And I found t1 previously from here. So the total time of flight is t1 plus t2. Okay. Another variation of this problem is, suppose I have a room, okay, and I'm throwing a projectile from the floor. U is fixed, but theta is variable. If theta is small, means the projectile will go like this and come here. If theta is large, means it will just go on hit the ceiling wall. But if theta is one particular value, you just go touch this roof and then come back. Okay, so and this height will be given. So for this particular one where is touching the roof, I can find the value of theta. Because u is given, theta I can find such that the vertical height, maximum height is this value h that is given. I think if you use the same formula for h, u is given, theta I have to find out. Everything is known. So h is given. So in this h will be given, which is the height of the room, and u is given, and g is known. So from that I can find sine theta. So from that I can find theta. So this is the room, and the height of the room is h, which will be given, and u is also given, and the vertical maximum height is the height of the room, which is known. So if I use that thing here, this formula for height, this one. So h is known, u is known. So I can find theta, sine theta. From there I get theta. Okay. Center of mass of system of particles is defined as you have two masses, say m1, m2. So the center of mass will be somewhere in between these two. If they're equal mass, means center of mass will be exactly in the middle. So if m1 is heavy, means center of mass will be towards m1. If m2 is heavy, means center of mass will be towards m2. So the center of mass, the x value center of mass is given as combination of x1 and x2. So and the weightage of x1 will be m1 divided by the total mass, and weightage of x2 will be m2 by total mass. Okay, so there can be more than two masses. It can be m3 and m4 and m5. So center of mass of this combination of this phi will be so x1 plus x2 plus x3 x4 plus x5, and the corresponding weightage. The weightage will be m3 divided by the total mass, which is m1 plus m2 plus m3 plus m4 plus m5. So the weightage here is m4 by the total mass. This weightage is m5 by the total mass. So that's what they given in the book, center of mass. Just so center of mass is defined, say there are n point masses and the locations are x1, x2, so on up to xn. The center of mass is this one. So this I can rewrite as x1 divided by some x1 into some factor, that's m1 by total mass, x2 into some weightage, which is m2 by total mass. Okay, so this is the mass are all placed in the x-axis, but in general it can be placed somewhere. So all the masses will have some x coordinate, y coordinate, and z coordinate. Z coordinate we have not given. So this is in 2D. Okay, so I can have x center of mass as this one, and y center of mass as this one. Similarly, z of center of mass also I can define like this one. Okay, so I can combine these three and write in vector form as this one. Center of mass is summation of mi r divided by the n. So once I have, say, let me take a simple case. M1 and M2. Say on the x-axis, suppose M1 is moving with some velocity, say 2 meters per second, and M2 is also moving with the velocity, say 2 meters per second. The center of mass will be somewhere, say M1 is heavy, the center of mass will be here. The center of mass also move with the same velocity. Velocity of center mass will also be 2 meters per second. But suppose I take a second case or second example, where the first mass is moving towards right by 2 meters per second, and the second one, the first one is say moving towards left. By 2 meters per second. And the second one is moving towards right. By 2 meters per second. Then the center of mass. Okay, even if we take a special case of okay, if we take a special case of M1 equal to M2, then in particular case I can say the center of mass will not move. Because I have two equal masses like this, or if I have two equal masses like this, the center of mass will be the same point. Okay, so in general, x of center of mass is m1 x1 plus m2 x2. Just say 2-point masses, it will be m1 plus m2. In that case, I can get the velocity of center of mass as m1 v1 plus m2 v2 divided by m1 plus m2. So I have to differentiate this one to get this one. So center mass is like it can be defined like this. Okay, so if I different both sides, I'll get this one. So from this, you get the velocity of center of mass as m1 v1 plus m2 v2 by m1 v1 divided by the total mass. Similarly, I can define the acceleration of center of mass as m1 v1 plus m2 V2 is a vector divided by M1 plus M2. If there is a third mass, I have to add M3, A3, and for end point masses, I have to add up to Mn. Mn, Am divided by the total mass. So given velocity of the individual mass is same, V1 and V2, I can find velocity of center of mass. So if the question they are given M1, M2, and also the corresponding velocities V1 and V2, I can find the how fast the center of mass will move. Center mass, velocity of mass. Work done by a force. So work done by a force is F dot ds. This is by definition. Okay. And if this force is a function of, it's a non-uniform force, means it will be a function of, say, x. For 1D, it will be, say, the 1D motion is in the x direction. In that case, the work done will be F into dx, because direction of force is also x, displacement also along x. So F into dx to cos 0. So the work done for the displacement along the x direction due to the force acting on the x direction is F into dx. So the total work done will be integral of VW between the initial position and the final position. So that will be integral of F dx between the limits x and x. Okay, so F as a function of x will be given. This function will be given. So you have to find the work done to go from one point to another point along the x-axis. It can be, say, from -1 meter to, say, 10 meters. Here, the force is a variable force. The force is a function of x. In the sense, the force is dependent on the space. So it's a non-uniform force. So F as a function of x is some curve like this. So using the definition that the force for a small interval is F into delta x or F dot ds. This is for a small interval. So if I add the work done for all the small intervals, I get the total work done. So this summation, okay. So when the interval length I make it very, very small, then we can define summation. So that summation, when the interval is very small, is the integral. So the work done is integral f dx. So the function f is a function of x will be given. Once that function is known, I can find the value of the work done. For example, here, f is given as function of x. Okay, it's a different problem. Okay, fine. F as a function of x will be given. So from there, I can find the work done by using the integration formula. Okay, the meeting will close in 1 minute. Rejoin again. Non-uniform, you have to do the integration. Speed time graph of a body falling under gravity. After that, conservation of momentum. Yeah, so this is the final thing. So, if you have x versus t graph, I can get the velocity graph as integral of x of t. And from velocity graph, if I integrate it, I can